Good morning, everybody. Welcome to class this morning. Thank you for joining me as we start Module 3 this week. So we will be looking at the idea of programmatic thinking. But before we get into that, just a couple of quick announcements here this morning. The first is that, I graded all of your Module 1 assignments earlier. Right, all of your essays. There were a lot of great essays that were turned in with a lot of really good ideas and a lot of really strong thought. So I really appreciate that from all of you. I'll be grading your Module 2 assignments over the next couple of days. Just a reminder that if you do so happen to do something early, I wait until things are due before I start grading things, just so everybody's on a level playing field there. So I'll be looking at your Module 2 assignments over the next couple of days, getting those graded. But this week we're on Module 3, which is Programmatic Thinking. And the big idea with Programmatic Thinking is essentially we're starting to learn something new. And I think that's important to kind of point out here. The high degree of likelihood that the vast majority of you have never attempted programming or coding or doing anything like this before. Right? This is a brand new thing for you to learn. And when we're learning something new, when we're learning anything new for that matter, the way we approach what we learn is important. Because we essentially have to approach this new concept as empty vessels, as empty cups, ready to absorb and learn new things. One of the things that we'll talk about today is just the fact that we can't expect to know everything right off the bat, right? We have to put in effort, and we have to try, and we have to learn. Which is one thing to say, we got to approach this from a certain perspective, but it's another thing to say, well, you might not do so great right off the jump. But that's okay. That's all a part of the process, and this is a process. Because really, when we're thinking about programming requires a special way of thinking. And as I mentioned, whenever we're learning something new, it requires a new mindset, right? Like, think about, every big milestone you've ever achieved where you've had to learn something new. Whether when it was when you learned how to read for the first time, when you were learning how to do complicated math equations, we've done addition and subtraction, and now we're multiplying and dividing. Wow. Or when you learned how to do more advanced things as you progress throughout your educational years. Right? Whenever you face these big milestones, you have to face them with a different mindset. And so when we're approaching this, we're thinking, again, I'm going to clear the slate. I'm going to look at this with fresh eyes. I'm not going to come into this with any assumptions. I'm not going to come into this with any preconceived notions. I am going to come into this with a willingness to accept things as they come and learn as I go along. And that's really a big thing here. And programming is really different from other things you could learn. Right? There was a study done recently. A lot of people think that your skills in math could correlate to your skills as a programmer. And to some degree, I could see how that thought process could work, right? Because like math in programming, there's a lot of logic. There's a lot of the ability to reason out and think through all these sorts of things, right? You have to be able to do things in a certain sequence. We call that an algorithm, which we'll talk more about in just a few minutes. So it seems reasonable when people say, oh, if you know math, you can probably learn programming. But I always kind of question that, and have in the past. You know, some of my past students might have heard me say before something to the effect of, if you can add, you can program. And one of the things that I've shown students in the past is essentially how that is true. I mean, when we talk about the mathematician Boole later on, when we talk about Boolean logic, they said that that you could solve any math equation with just a series of true or false questions, right? So if we can solve any math equation with just any true or false questions, then math maybe isn't that hard. And I contend that all of math is addition, right? When we get down to these basic mathematical operators, we can add, we can subtract, we can multiply, we can divide. And really all of that in its core can be broken down into addition, right? Like addition, subtraction, and multiplication are easy ones. Division is a little more complex, right? But think about it. Like addition's obvious because it is addition. Subtraction, well, you're not really subtracting, are you? You're adding a negative number. So that's addition. Multiplication, you're just adding something multiple times. And division, you're just keeping a tally through adding how many times one number can fit inside of another number. So all math is essentially addition. And I might even show you a little algorithm for how we can solve that division one when we get to the next module. But I read a study recently that I thought was pretty interesting, and it made a lot of sense. It was from within the last couple of years. I don't have it at hand here to remember who exactly published the study. But it said that your ability to program actually has a closer proximity to your ability to learn another language, something like Spanish or Japanese or Italian. Right? And, you know, I was talking to one of my other students recently, and, you know, we had just introduced some programming concepts for the first time. And they were just like, you know, this sounds like Chinese. Like, this sounds like some foreign language that I'm not at all familiar with. And yeah, it is. Right? We're going to use terms that you're unfamiliar with. We're going to use essentially sentence structure, this syntax that you're not familiar with. Right? When we get into programming, we talk about our data structures, and these data structures function like a lot of the things that we use in the English language and in other languages where we talk about things like, oh, subject-verb agreement, subject and predicate, adjectives, nouns, you know, parts of speech, these sorts of things, right? There's a lot of interplay here, and there's a lot of close ties, right? So when we think about programming, think about whenever you first tried to learn Spanish, or whenever you first tried to learn whatever your foreign language of choice was when you were in school, or maybe you haven't done any foreign languages yet. But what foreign language you might want to learn, it's going to follow along those same lines. So what I'd like to start out with today is sort of challenging you to change the way we think as we approach this new opportunity. You know, I don't like to call things difficult, right? I like to call them challenging. That's something that I mentioned in the past, right? So what we're doing as we approach programming from this new mindset is we're approaching a new challenge. And so we need to change the way that we think before we approach this challenge. And I have a few little tips here for us to be able to do this. One is to write things down first. Like, this seems kind of silly to some people before they realize just how important it is. Because, you know, speaking of language, like, we come from this mindset of when we write a paper, we're going to create a plan, right? Like, that's something all of our, you know, middle school, high school, English teachers, they all approached us. And, you know, when we're learning how to write essays, when we're learning how to write papers, they say the first thing that you do is you make an outline and you make a plan, and then you can start filling in that outline. And they make us turn in outlines, and we think, this is silly, this is busy work, I could just write this. Maybe you could. But maybe if you took the time to sit down and think things through and plan things out, you might actually end up with something more robust, something that maybe you didn't look over, some things that you might have otherwise if you sat down and you made yourself a plan. And so when we're talking about programming here, we talk about that in the same sort of way. We start with a pencil. You know, we take some time, we sit down, and we start writing out the exact steps that it takes to solve this problem. When we call that an algorithm, right? We'll talk more about that in just a few minutes. We call this an algorithm, the steps that we take to solve a problem. So before we go and we start to write code and we start to commit things to a programming editor and we make a bunch of mistakes and try to fix them, we need to sit down and we need to think about, well, what is the problem? What is the thing here that I'm trying to solve? And what are the steps that I need to be able to do in order to solve this problem? Right? And just take the time and you write it out. It might take you a little extra time up front. Right? It might take you a little extra time in the beginning. But when you're actually coding and writing things out in your program, it'll save you a lot of time there. And that's the big important thing, right? Is that you're saved that time when you're actually putting in the effort. You know, there's actually, and this is just kind of an aside, there's actually a word or a name for this sort of propensity that we all have just as human beings to skip past the instructions, skip past the introductory phase, skip past, you know, the planning phase, and just jump immediately into trying to do something, right? Like, it's a phenomenon that we all encounter. Like, you go to IKEA, you get a piece of furniture, and you're like, I don't need these instructions. You throw them to the side. I can just build this thing, right? It's just 6 parts with some screws. I can knock this out, no problem. And then, you know, 3 hours later, when you have nothing close to what the picture on the box looks like, you give up and you go back and dig those instructions out of the trash. We call this quick start mentality. Right? So right off the bat, this is something that's kind of ingrained in human nature. Like, it's something that we all do. So right off the bat, we are going to be fighting against something that's ingrained in human nature. This idea that people engage in this sort of quick start behavior. So the very first thing that we're talking about when we're talking about how to change our mindset to approach programming is essentially counterintuitive to human nature. So it's going to be difficult. Right? It's going to be a challenge in that. But write things down first. Another thing is that programming requires precision. And we mentioned this before about how programming requires precision. I said back in Module 1 when we first started talking about this idea that our computers are dumb and we are not dumb, we are smart, that we'd revisit this concept a little bit later, and now is the time. Right? Programming requires precision. We are smart. You're smart. I'm smart. Everybody that's watching this, we as human beings are smart. Our computers are dumb. Our computers are not smart. I think oftentimes we get kind of caught up in this idea that our computers seem smart. Right? Like they can show us anything we want to know. They can do any task for us that we want it to do, but we have to be able to tell it what tasks to do. A computer is a machine. It's completely void of reason. Nothing that we do can make our computers understand us. We have to give explicit instructions to our computers. So it's important that we're precise with the words that we use. But more than that, it's also important to be precise with capitalization and punctuation. Because our computer has a limited understanding. Our computer looks at things in only one certain way. It takes everything that we put into it and it breaks it down into a series of electrical impulses that we can make resemble ones and zeros, right? Everything's either on or off. So it either gets a little electrical impulse that it sends down a line or it doesn't. So in order to make these instructions clear, we have to be precise. And, a large part of this, which is what we talked about before, is because of how our computers look at letters. And we talked before about this idea of the Ascii table. Right? Computers use binary and they use Ascii, what we call Ascii Lookup tables, to convert characters to something that they can understand. Right? Because our computer doesn't understand words. Our computer doesn't speak English. Our computer is a machine. It understands electrical impulses. It understands electricity. So when we type in a letter, our computer takes that letter and it breaks it down. It compares it against one of these Ascii lookup tables so it can find what that means to them, and it can in turn takes that and converts it into a series of electrical impulses that are represented through binary ones and zeros. So our computer can go, oh, you mean blah. So let's just take a quick minute here and just look at our Ascii table and examine how these characters are converted to binary so we can have this better understanding of what's going on and the importance of precision. Right? So this is an Ascii lookup table. This is what our computer uses to go in and convert the characters that we type into our computer into something that it can understand. And I want you to notice something over here. Right? Over here along the left side down through the first one here on the second column. We have tabs and we have shifts and we have carriage returns or line enters, line breaks, backspaces, spaces, escapes. These aren't even regular characters. These are just spaces or parts of formatting that our computer has to be able to break down and understand. So it doesn't even understand line breaks without having to convert it to an Ascii table, for example. And we see things like one of the things that we talked about before was this idea that our uppercase and our lowercase letters are two separate things, right? Like if we look over here, we can look at, say, our lowercase b, and our uppercase b. You know, you and I look at lowercase b and we look at uppercase b, and since we're smart, right, we have the ability to reason, we have the ability to understand, we have the ability to know things. We look at these two characters and we say, that is B. They are both B. I am a human. I am smart. I know that they are both B. They are B in different forms, but they are both B. Our computer doesn't understand it to that level, right? Our computer compares it against this chart. So when our computer sees our lowercase b, it's not seeing that. It takes this symbol, brings it into this table, looks it up, and it sees that our lowercase b is actually the number 98. Our uppercase b, conversely, it sees that, it takes it, goes into this table here, finds it, there it is. It sees our uppercase b is 66. Right, so that's 32 numbers, 32 digits. Or not exactly 32 digits. That's a difference of 32 is what I'm trying to say, between uppercase b and lowercase b. So they're not even close. Right? Uppercase F is closer to uppercase b than lowercase b in the mind of my computer, which is kind of difficult for us to comprehend. What makes it even wilder is when we take this and we break it down into those electrical impulses, into that binary. Right? So if we look at this, right, we said our lowercase b was 98. Our uppercase b was 66. So let's take these and let's break them down into binary. And we break our binary down. A single character of binary is called a bit, right? And there are 8 bits in a byte. So we need a series of 8 ones or zeros to encode 1 byte, and we can encode 1 character in 1 byte. So it means we need one of these octets of bits, one of these series of 8 ones and zeros, to be able to encode our lowercase b or our uppercase b or any of our other characters. And right, so, and you might be familiar with our standard decimal number system, yes? Like if we look at a number like 1,000, each of these numbers in our number 1,000 has a place. Right? We have our first number here, that's in our ones place. Our second number here, that's in our tens place. Our third number here, that's in our 100s place. And our fourth number here, that's in our thousands place. And that makes sense, right? Because our number system that we generally use is a base 10 number system, 0 through 9. So when we're moving places and going to the next place, we're multiplying by 10. So we go from 1 to 10 to 100 to 1,000. However, what we're working with our computer is a base 2 number system. So when we go through each place, we're talking about multiplying by 2 each time. So if we break these down, for example, right, we can take our octet and we can break it down Let's create a little space here. There's 1 segment, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. There we go. That's what we want. Right, so just like with our decimal, our base 10 number system, we start with a 1. So that's our ones place. Then we say 1 times 2. Well, that's 2. 2 times 2, that's 4. 4 times 2, that's 8. 16, 32, 64, 128. So these are our places in our octet, in our base 10 or base 2 binary number, right? Instead of a 1s, 10s, 100s, and 1000s place, we have a 1s, 2s, 4s, 8s, 16s, 32s, 64s, and 128s place. Right, so for all my Minecraft players out there, like this might look a little similar to you, right? Like everything here is broken down into, you know, like the stack size for Minecraft, right? 64 in a stack, 32 half stack, 16 quarter stack, or a stack of certain items, right? And this is the same reason why those are the basic numbers used for stacks in Minecraft. It is for memory management purposes, right? Like we can take everything and we can put it neatly into, you know, one of these places if we use this sort of stack size. So we're not doing, you know, complicated math, if you will. So now the challenge is to take something like B, which we said has the decimal number of 98, and convert it into binary so that our computer can understand it. So let's start with this one, and we'll also do our 66 as well. Right, so essentially all we do here is we're going to go from left to right, starting with 128, and just see if we can take our number that we're starting with here, which is our 98, and subtract our place value from it. If we can, then that segment gets a 1 because it's true. If we can't, that segment gets a 0. Right, so let's just start with some running math up here. We're starting with our 98. 98 minus 128 puts you in the negative. It doesn't go in there, so that is a 0. 98 minus 64, however, that does go in there. It does fit in. And then we can do our math here. So we get rid of... So now that we've put a 1 here, we've gotten rid of our 64 out of here. So we can change that, subtract that. Now we have 34 left. 32? Absolutely. Subtract 32. That leaves us with 2. 16? Nope. 2 minus 16 goes negative. 2 minus 8 goes negative. 2 minus 4 goes negative. 2 minus 2, yes. And that leaves me with 0. So anything else goes there. So when our computer sees the lowercase b, it sees 0, 1, 1, 0, 0, 0, 1, 0. To encode that character into binary. Conversely, let's have a look at our uppercase b. Let's just draw ourselves another little series of boxes here, just to help ourselves keep it organized. So we're looking at our uppercase B now, which starts us with 66. Well, that's still a 0, because 66 minus 128 takes you into the negative. However, 64 does go in there, so that's good. We can put a 1 there. But all of a sudden, we're only left over with 2. We got 2 here. So everything else becomes a 0. Now, once we do this, we can see this encoding maybe make a little more sense, right? Because in the decimal, we're 32 off. But in our binary here, we're only 1 bit of difference. Here in our 32's place. We're only 1 bit of difference between that lowercase b and that uppercase b. But that 1 bit of difference is significant. That 1 bit of difference is enough for my computer to say, okay, this is this versus this being something else, right? It's 1 bit of difference, a bit being the tiniest amount of memory that we can have, but its significance is huge. So that hopefully shows you why exactly precision is such it has such importance as we're programming. You know, just that one little bit of difference, that one teeny tiny change converts something that our computer understands as one thing into something completely different and foreign and strange that it might not be able to connect. So, for example, like if I have a word that starts with a lowercase b, and then I try to use that word later, and try to start it with an uppercase b, my computer will look at that uppercase b word and be like, what is this? I have no idea what this is. You've not told me about this before. Even if it's the same word structure, like if it's lowercase b build versus uppercase b build, and you said, hey, lowercase b build is a thing, well, that doesn't mean uppercase b build is a thing, right? We have to be precise. And in general, we don't have to be precise a lot. Like, that's something that we're not in a habit of. We're not in a habit of precision. We're in a habit of getting close. Right? We're in a habit of being good enough. But in this instance, close and good enough isn't going to allow us to work things out. Now, the next thing that we have here is pretty critical, and it's going to sound strange at first, but I will explain it to you. Get comfortable with not knowing. And this is probably the most challenging thing we can do, right? Is this idea of getting comfortable with not knowing, getting comfortable with the fact that you're not going to know everything that you need to do immediately. Getting comfortable with the fact that you have to learn. You know, by default, again, it is our human nature, right? A lot of stuff that we've talked about already is against human nature, which is why it's so important that we think about these things in relation to programming from a different mindset. It's against human nature to accept that you don't know something. We all want to be good at everything, right? If it's a task that we want to do, we want to be good at it. That's human nature. If I'm going to do it, I'm going to try to be good at it. I'm going to try to do a good job. And if you're not good at it, or at least if you're not good at it right away, it can be disappointing. It can be disheartening. And so the idea here, and it sounds kind of one of those things that's easy for you to say, right? Like, it's easy for you to say, get comfortable with not knowing. Because you're the one that knows it. Like, you're the one that's the teacher. But, like, especially in this industry where things are constantly changing, or there's just this huge breadth of stuff that you need to know in the world of programming. There's still stuff to learn every single day. And people that have been programming for 10, 15, 20, 30 years still have stuff to learn every single day. You're not going to know every single thing. The more you do things, right, the more you'll learn and the better you'll get and the more you'll be able to accommodate. But you're probably just not going to be good at it right away. And, we as human beings get this desire to know. Right? We want to know. We want to know. Even when we don't know, we want to know. Right? And it's these types of things that lead us to what they call existential crises. When we want to know something that we don't know yet. And in this instance, it could lead you ending up like this guy. Right? I know I've had these moments before, where everything is miserable, everything is bleak, everything is dark, like nothing is working. I've tried everything and nothing is working. Programming's bad, or I'm bad, or whatever, like this inadequacy. And then it turned out, oops, I just wasn't as precise as I should have been. I misspelled a variable. I can't tell you how many times a misspelled variable has taken down a program. It's happened to me, and I've seen it happen a bunch. So these two things are tied together. This idea of getting comfortable with not knowing and, being precise. Because again, precision is not in our human nature. None of this is in our human nature. So we're experiencing things and we're trying to think about things in a way that we're not used to. We're trying to do things that we don't know how to do. We're trying to think about things in a way that we're not accustomed, or wanting to know things that we just don't know yet. And it can get discouraging, and it can tear you down, and it can break you or close to it. But the goal here is not to give up. These issues, these problems, these things that are against human nature are overwhelming to us. Or they can be. Right? And when we get overwhelmed, as we are wont to do, right? Again, human nature. The first inclination is to throw up our hands. Say, you know what? I give up. This is too hard. I can't do this. I don't know the things that I need to know. I don't know it. I'm just going to go ahead and throw in the towel. Right now. And that's not coming from a place of incapability. You're not incapable. It's coming from a place that includes a lack of comfort from not knowing. It's coming from a place that maybe requires you to think about precision when you're not accustomed to it. It's coming from a place where we're having to think and behave counterintuitively with human nature because we're smart and our computers are dumb. In a way, we have to think about the way our computer thinks and put ourselves in our computer's shoes, which is counterintuitive. And so when we push through, like, you immediately give up. Maybe you just try to get help. You try to get somebody else to do it for you or whatever. That's not going to get you anywhere. Right? My suggestion to you all is not to ask for help right away at the first sign of getting overwhelmed. Right? Because again, this is about retraining your brain. So to some degree, we need to be able to push through. Because as much as our struggle tears us down, as much as the struggle just depresses us or is disheartening to us, the breakthrough, when we've actually made this connection, when we've actually gotten over this hurdle that is counter to our human nature, the breakthrough is much more rewarding than the struggle is disheartening. But if all else fails, ask for help. Right? If you've tried several different ways and you're just not getting it, if you're just slamming your head into the wall over and over and over again, and you're just not understanding it, that's okay. Right? Ask for help. That's what I'm here for. Your classmates might be willing to help you if they're getting on it quicker. As much as getting comfortable with not knowing and trying to push your way through these hurdles is important, it's also just as important of getting comfortable seeking out help when you need it. And that could be asking me, that could be a Google search, right? Like, again, the possibility of you knowing everything, super, super low, right? But the possibility of somebody in the entire world having encountered your problem at one point, higher. So there is that. So what is an algorithm? Right, now that we have this idea of what our mindset should be, how we're going to try our best to push through, how we're going to be precise, how we're going to get comfortable when we don't know something so that, we're not coming down on ourselves even harder. Let's change our focus, and let's actually talk about some more programming related things, like what is an algorithm? In general, when we think about algorithms, you hear them mentioned in movies or on TV. We conjure up in our minds something super complex, something that only like a brilliant scientist could conjure up. Right? Somebody standing in front of a chalkboard and just scribbling numbers and letters in some sort of weird sequence until they just go, aha, that's it. That's the algorithm. But when we take and we strip all this sort of mystique away from the idea of an algorithm, it's a simple concept. Right? An algorithm is nothing more than the steps that we take to solve a problem. It's just the steps that we take to solve a problem. You know, just like I mentioned earlier, if you get a piece of furniture from IKEA, something like that, you know, some of that flat pack furniture that you have to put together, what comes with that? An instruction manual. Right? And so when you are solving that problem of trying to get these pieces of particle board to look like that picture that's on the box, you follow the prescribed steps to get from that problem state to that goal state. That's all an algorithm is. It's just those prescribed steps to get from a problem state to a goal state. So when we're scribbling things down, when we have our pencil out and we're writing down our problem and how we plan to solve it with our program, essentially what we're doing there is we are writing an algorithm. So this is the thing that we want to figure out. You know, the steps that it takes to solve our problem. We want to figure that out before we commit a single word of code into some kind of code editor. Now, when we're thinking about designing an algorithm or creating an algorithm, there are three important factors to consider. One is that the algorithm must be well defined. Two is that the algorithm must be clearly given. And three is that the algorithm must solve the problem. So let's look at these. One is that the algorithm must be well defined. And so when we're defining our algorithm, what we're talking about there is what our problem is, or what our goal is, right? Problem and a goal is essentially just two sides of the same issue. Right, on one side we have the problem state, we have the issue, we have the thing that needs solving. And on the goal side, we have that solution state. Right, we have the aftermath, the desired position that you want. So it's really, you know, when we talk about a problem that we're defining or a goal that we want, you know, it's really a part of the same issue. You know, how do we get from beginning to end? What is the program trying to accomplish? So in order to make sure that your finished program actually makes sense and can work to solve the problem, you have to be able to clearly define the problem. Where am I starting? Where am I going? Now, how do I get there? Next is that the algorithm must be clearly given. You should be able to take the steps you're approaching to solve a problem and give them to someone else. Right? This is the crux of your discussion assignment for this module. Is that you should be able to take the steps that you're given in an algorithm, hand them over to somebody else, and they should be able to solve that problem using your algorithm. So we take it and we kind of use our discussion here to kind of break this issue down into something that's a little bit silly, right? But it is something that gets us used to the idea of writing writing these series of steps for some common everyday problems. And so when they're solving that problem using the algorithm that you've given them, they should be able to solve that problem only using the algorithm that you've given them. Right? You have to make sure that you didn't skip any steps. You have to be specific. Right? Because like when you think about your discussion assignment, Think about you're taking these instructions to, one of these everyday common problems, and you're handing them to somebody that's just come down from the moon, let's say. Can they follow these instructions and kind of figure things out? Because that's what we're doing when we write a program, essentially. We are creating a series of instructions, and then we're handing it to a moon person that doesn't have our same intuition. Right? Our computer is that moon person. Our computer needs us to give it specific instructions in a specific order for it to be able to solve the problem. And that's what we're talking about here. So if up front we design this algorithm and we sit down and we make sure that every step that we need to include in order for this problem to be solved is clearly given, then we know nothing's been skipped, nothing's been overlooked, nothing's been left out, and our computer will have an easier time understanding it. Finally, the algorithm must solve the problem, and I don't know how many times I've seen this issue, where the algorithm doesn't quite solve the problem. It gets you almost there, and then it takes a left turn and it goes somewhere else. You want to make sure that your algorithm meets the goal. And by and large, the problem with this happens when we encounter something that we call scope creep. Right, where our scope of work just starts expanding because, we've decided that we want to add this feature, and then this feature, and then this feature, before we're finished solving the original problem. It's all well and good to add features, but if we start pulling in things to add new features before we have the original problem solved, we can lose sight of that original problem. And then all of a sudden, the algorithm and subsequent program that we make doesn't solve the problem. Focus on that problem. Focus on that goal that we defined back here, right? We made sure this was well defined. Focus on that. Solve that. Make that. And then if you decide later on, I want a feature that does this, that's a new problem. And how can I accommodate this new problem with a new algorithm into what we have? So code, solve your problem first, go back, refactor, add things later. We're running out of time in our hour here. So instead of spending time with events and variables and control structures, I think I'll just let you watch and read the material that's in the module for those. Right, each section of these data structures has a little video that goes along with it to show you how to use it in these block logic type programs. However, I would like to show you this block logic stuff. I wish I had more time to do more stuff with the block logic before we push on to the next thing. Right, so instead we just kind of introduce it, and it's a good way to practice. And so that's more or less what I'm trying to encourage you all to do with the block logic stuff, is as you are trying to figure out these data structures and trying to figure out how this stuff works. We might even get into the JavaScript module, way later on down the line, which is going to be module 9. Right? And a lot of these data structures are going to be rearing their heads again. And it's going to be how did a loop work exactly? Let me go back and look at this block logic again, just so I can get that visualization of what's going on here. So I'm going to jump over to my Scratch window now. That's scratch.mit.edu. The direct link is in that begin here module if you want to use it. And we'll sign in. And so after you sign in, you see something that looks like this. What you want to do is you want to go up into and create a new project here at the top. Create that project. And then it'll give you a window that looks like this. And this is our code editor for using our block logic. And we see over here on this left-hand side, we can see a lot of these terms that sound familiar if we read and watch our module. Things like events, control, operators, variables. Right? So for example, we always start with an event. We'll start with when an event is just something our program is listening for. Right? Things like clicks and key presses and time passing, all this kind of stuff, right? So we can have it when our green flag here is clicked, or we can have a key press. Let's add a key press event here to what we have. And we can make it any key. We'll just make it space for the time being. And from then, when we start to add our control structures, and we see things like our loops. And in our loop here, it's called repeat. So if we want to do something over and over and over again, we use our repeat loop. And it'll allow us to do something multiple times. And so when we're using this block logic, one of the things that we see here, right, is we see that these little blocks have these little tabs that allow them to slide into one another like puzzle pieces. So this here is what really gives us that good visual of how all this stuff works together, right? Like if we just write a bunch of code, we can understand logically that things work from top to bottom. But when we get into these data structures, into these decision-making structures, that's where things start to become not quite as clear. Right, so for example, I could put something in here, right? Like we see this little open area here, which is implying that we need to be able to put something inside of it, right? So maybe we need to add some kind of motion here, like maybe we'll move them 10 steps, move our little character 10 steps here. Now, if we take our loop out of the line, and we do that, we come over here, we press our space key, we see that it makes a slight motion. Right, and I'm going to reset him by just clicking the sprite, moving him to 0, 0. Right, so now we have something, a little function here that'll reset our sprite. So whenever we hit our space bar, he'll move. Whenever we click him, he'll reset. So whenever we move him 10 spaces, we see he goes 10 spaces. But whenever we add our loop into the mix, and we see that there, so our move 10 spaces goes inside of the loop. So every time it repeats, he'll go 10 more spaces. We see he moves a lot further because he went 10 spaces 10 times. So he moved 100 steps. Click him to reset here. We can even add things here, like in our control structures. Conditional. And in this conditional, we can also put our loop. Right? Our conditional statements, also known as if statements, allow our computer to make decisions in a program. So if one condition is true, then it'll run the code. If it's not true, it won't run the code. Right? So we can have a look at that via operators. Right? So we can put just one of these operators in there, like we can see the same shapes work. In this case, it's if blank is less than 50. We'll repeat 10 times, moving 10 steps. So we can see here, we can put something in like if 10 is less than 50. which it is. Now it's still waiting on that key press. It's still waiting on that event to happen before anything happens. So until I press that space key, nothing will happen. But when I press that space key, we can see that it moves. Let me reset him. But if we change that value here and said something like if 60 is less than 50, well, it isn't. So when I hit space now, you know, you can see up here, you can see these buttons lighting up for a second. But it doesn't do anything because that condition is false. So it just skips over that block. Right, and so this gives us a visual indicator of how all this looks. Right, our if statement wraps this loop, which is our repeat statement here, which wraps an instruction. And we can even use variables here. Variables are pretty interesting. When we think about a variable, and we'll talk about variables more in depth in the next module, a variable is just a container that stores data. And so that's essentially what I'm doing here is I'm creating a container, and I can make a new variable and I can give it a name. And now I have it here. Now in this program, I could add a set my variable. So we'll have a set my variable here. Instead of this, though, it'll be the one that I've selected here. Select set num to 60. Right, so now we have this data in a container where we can take and use this value instead of the number. And maybe I want them to move that num amount of spaces if it's true. Right? So another big thing to point out here is just this structure. Right? This structure is something that's important for us to notice. How all these puzzle pieces nest and are shaped in and out of one another here. Right? Where one thing's going, where another thing is, so on and so forth, right? And we can see based on these little tabs the directionality of where we're going. We can see how they nest inside of one another. So now our variable num is set to 60. So we're saying num, which is currently 60. We're going to move that many spaces. But if we hit space, right, it sets num to 60 here. We can see what our value num is in a specific place. So right now, num is 60. If we keep hitting our space key, nothing happens because num is 60. However, if we shrink it down to 10, well, num then becomes 10. So if we hit space, we're moving 10 times 10 here. That's 100. 10 here. We reset that if we change this to 30. 30 is less than 50. And we're doing 10 times 30, so now he'll move even further. Moves right off the screen there. Let's see if we can still click him. Good, good, good. We can even change the value that's in our container, right? We can say, okay, well, what we'll do here is we'll say, right off the bat, num's going to equal 10. If num is less than 50, well, let's change our num variable by 10. So let's add 10 to it. So we're not doing as much. Let's repeat this 3 times. And now we have this. Right? And so you can watch here when we hit our button, when our space key is pressed, it'll set num to 10. Then it'll turn around and say 10 is less than 50. Then it'll change the num and add 10 to it to make it 20. And it happens so fast, it doesn't really change our number here for us, but that's what's happening, right? And we'll go over that more in our next module, and go deep into what is happening here. So this is where we'll go ahead and we'll stop the video for today. All right, we covered a lot of material today. We'll hang out in the chat for just a couple minutes with the music playing, just to see if anybody who's here live has any questions. If you're watching this later and you have questions, please send me an email, send me a Teams message, just contact me. That's all that I have for you for today. Thank you for watching. We'll see you next time.